Okay, so today we're going to talk about degree of freedom analysis. And essentially, it's a very powerful tool for thinking about any kind of engineering problem. And particularly in this class, it allows you to very quickly figure out if you have enough information to solve the problem, and if not, what kinds of information you need. And when we get into more complicated systems, we have more than one process or more than one box, it becomes even more useful because it can help you figure out where to draw your system boundaries. So I'm just going to give you a very, very simple problem to try to explain how degree of freedom analysis works. And essentially what I'm going to show you is sort of a shortcut way to do this. But before I show you the shortcut way, I'm going to show you the long way, which is probably something similar to what you may have learned in math. So let's suppose we have the system, and all that's happening is that fluid is flowing in, stream F, and we're going to call that water, and we're going to say that we know that 1 gram per minute of water is entering that system, and water is coming out. So that's about as simple as it gets. Now, if we assume, well, first of all, if we go ahead and write the general mass balance equation, we know that these are 0 because there's no reactions. And let's assume it's a steady state. So we have in equals out. So basically degree of freedom analysis is simply counting the unknowns and the knowns. Okay, so the unknowns are the mass flow rate of water in F and the mass flow rate of water in P. The knowns are that in is equal to out. That is the law of mass conservation. And we also know that F equals 1 gram per minute. So basically, if we go to the next page, we can draw this up as, I like to make a little table here, where you count the number of unknowns. In this case it was 2. We put a plus sign there, and then we're going to subtract the mass balance equations. So we could have more than one independent mass balance equation. In this case we only have one. And we can subtract any other specifications. And we have one specification. So a specification is basically any other independent information that you can use to solve the mass balance equations. So 2 minus 1 minus 1, and then we can write down here the degree of freedom is equal to 0. So that is obviously a very simple problem. And what I'm trying to help you do is be able to draw a chart like this really simply without first having to write out all the mass balance equations. Well, actually, we never did write out the mass balance equations. So if you were to, one way of figuring all this out would be to write out all your equations and count your unknowns. So if we were to write it in terms of n equals out, this would have been another way to do this. We could say the mass flow rate of F is equal to the mass flow rate of P. So these are your 2 unknowns. And then, of course, you have one equation. These are your knowns. plus we know that F is equal to 1 gram per minute. So let's go to a slightly more complicated problem. Suppose we have water coming in at 1 gram per minute. And suppose it's coming out in two different product streams. So we're going to call that product 1 and product stream 2. So this would be what's called the splitter, because there's nothing changing with respect to the composition. All that's happening is that the flow rates are being split into two. So again, if we're assuming steady state, and there is no reactions, and as I said, we're assuming steady state. So again, we have n equals out. So what is the equation for that? The mass balance equation for that is that the flow rate of F is equal to the flow rate of P1 plus P2. So we have three unknowns, and you have one equation. So what is the degree of freedom for this one? Again, you can write it up like this, and we could just shorthand write unknowns. We have three independent mass balance equations. We have one. And so, but we actually forgot one thing that we do know is we know that we have 1 gram per minute. So that's another known. So the specification that we have is that the flow rate of stream F is 1 gram per minute. So actually the degree of freedom for this problem is going to be 1. So what that means is there's no unique answer to this problem. Okay, so it's kind of like you could write the solution in a one-dimensional form, where if you happen to know one of these other unknowns, let's go back. We know what F is equal to, so if we knew what, we could plot P2 versus P1. That would be one way of showing the solution. Another one would be just pick a, say that P1 is equal to 0.5 grams per minute. That would bring the degree of freedom to 0, meaning that there's one unique solution, and that is, of course, if you go back to the equation, if F is 1 and P1 is 0.5, then P2 has to equal 0.5. So if we were to plot this solution, okay, it's going to look something like this. If P2 is 1, P1 is to be 0. Okay, so this would be the solution. And so if you have a degree of freedom of 1, you can actually plot the solution like this. All right, so now we're going to go slightly more complicated. Now suppose we have a mixer. And we have 2 feed streams. And 1 product stream. And suppose we have water coming in here, and we have ethanol coming in here, and so we're going to have both water and ethanol coming out. So, again, if we assume that, first of all, there's no reactions going on. And if we assume we're at steady state, accumulation is going to equal to 0. So again, we have n equals out. So the mass balance equations that we can write for this are what? Well, you can write one independent mass balance equation for each species. So we have 2 species. We have water. And we have ethanol. And I'm going to abbreviate ethanol ETOH. And so it's n equals out. So what you can write is F1, which is all water, is equal to whatever the mass fraction of water is in the stream P. Or I'm just going to write the flow rate of, use the subscript W here to indicate that we're talking about the flow rate of water in P. Or you can write it as the mass fraction of water in P times the flow rate of P. Same thing for ethanol. Similar thing for ethanol. Okay, so how many different unknowns do we have in here? Well, let's circle those in red. We don't know the flow rate of water. We don't know the flow rate of ethanol coming in. And we don't know the flow rate of water coming out. And we don't know the flow rate of ethanol coming out. However, we do have two equations. So if we were to again write that as in this table, the number of unknowns we'd have would be 4. The number of independent mass balance equations we have is 2. I didn't actually give any specifications this time. So the degree of freedom in this case would be 4 minus 2 minus 0, so it's 2. So what that means is if we specify 2 unknowns, we can solve for the rest. So if you go back to this thing, if we were to say, okay, we got, I'm just going to make something up here. Suppose we have 1 gram per minute of water coming in, and suppose we have 2 grams per minute of ethanol coming in. Well, using these 2 equations, we now know that the amount of water coming in is going to be 1 gram per minute. Darn it. And we're going to know the amount of ethanol coming in is going to be 2. So you can see we know everything there is to know about the mass flow rates in this stream. Okay, so now I'm going to show you. So that's basically how degree of freedom works. And the shortcut way to do this, and these are all very simple problems, of course, but I'm going to show you how you do that without writing out the equations. So I'm just going to repeat what we had in the last problem. Okay, so that's the drawing for the problem as we were initially drew it up. So basically the number of unknowns, once you completely write out your diagram, it's very easy to count the unknowns. It's basically what you do is you count the number of species. Actually, let's try that again. You count the number of species in each stream. So if your diagram's written out correctly, it's very easy to do. You get 1, 2, 3, 4. So that's how many unknowns we have. As far as the mass balance equations, this, you count the number of species. Associated with the system. So you should always draw your system boundary here. And you go around, and basically we have water and we have ethanol, just two different species. And that is the degree of freedom. Now, the last thing you want to do actually is count the number. We kind of got carried away there. You want to count the number of specifications, and then you go down, and then you can calculate the degree of freedom. Well, specification in this case would be, do we have any masses, any mass flow rates that we know of? No. Do we know any mass fractions? Well, we don't know these. That's why I left them in symbolic form, so we don't know what those are. We do know what the mass fractions of water and ethanol are in streams F1 and F2. However, we already know that the mass fraction of every stream, the sum of the mass fraction of every component in a stream, has to equal 1. That is by definition. So the fact that we only have one component in that stream and their mass fraction of 1 is actually not new information. That's sort of, so we don't count that as a specification. So there we have a degree of freedom of 2. All right, let me just say one last problem I'm going to make up here. And we're going to say this is a mixer. I'm going to make this quite a bit more complicated. Let's say we have A, B, and C. And these are the mass fractions. And this is stream F. And then suppose we have coming in stream B, we have B. And let's suppose B is coming in at 5 grams per minute. And suppose we have coming up here stream M. We have A, B, and C. And let's say we know that B is 50% by weight. B, and then coming out we have a product stream. So looking at this, obviously we're going to know, assuming there's no reactions, this is what we're assuming, and we're assuming it's a steady state. You're going to have A, B, and C coming out. And let's say we happen to know that the flow rate of this stream is 10 grams per minute. Okay, and we happen to know that the mass fraction of C in this stream is 0.4. Okay, so what's the degree of freedom for a system like this? Let's go ahead and put our system boundary around there. And then let's go down here. So this would be a real pain, to be honest, to write all the equations out and count them all up. And so we're going to use the system that I just taught you before to very quickly figure out the degree of freedom. So we always are going to count the unknowns. Then we're going to subtract the number of independent mass balance equations, and then we're going to subtract the number of specifications. In this case, we have both mass fractions and we have mass flow rates as specifications. We're going to count both of those up, and then we'll know what our degree of freedom is equal to. Got a little problem there with my page turning. Okay, so the number of unknowns, and I'll count that up dark blue. I'll just check them off. Okay, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 unknowns. Okay, the number of mass balance equations we can write is equal to the number of species. So A, B, and C. We just have 3 species. So we can write 3 independent mass balance equations for this problem. Okay, let's see how many different mass fractions we have that are independent. Well, we have 1 right here. 2 is 0.5 B in stream N. That's a second independent mass balance equation. Does this one count as a third? No, because we know that the sum of the mass fractions is equal to 1 in each stream, so that's not an independent piece of information. However, over here we know that A has a mass fraction of 0.1. That's our third independent piece of information. We know that B has a mass fraction of 0.2 in the stream, so that's the fourth piece of information. And C has a mass fraction of 0.7. No, that does not count as independent, because remember, the sum of the mass fractions is equal to 1. And if we have 3 components in a stream, and we know that 2 of them have a mass fraction combined of 0.3, we know the last one has to be 0.7. So that is not independent. So basically, we have 4 pieces of information there in terms of mass fractions. Okay? And we have, finally, we can look at what we have independent information for mass flow rates, and so you can see you have one right here. P is equal to 10 grams per minute, and another piece of independent mass flow rate here is B, it's 5 grams per minute. So we have 2 independent mass flow rates, and so the degree of freedom is to be 10 minus 3 minus 4 minus 2. So 10 minus 3 is 7, minus 4 is 3, minus 2 is 1. So that means there is no unique solution again. So if we wanted to find a unique solution, we need one more piece of information. So for example, if we could solve the problem if we asserted that, or suppose we found out that the mass flow rate of F is equal to 1 gram per minute, then that would bring the degree of freedom to 0, and there would be one unique solution at that point. So I'm going to leave it to you to prove that to yourself by actually trying to solve that problem. I think would be the best way to really learn this. So that's degree of freedom. I have an entire course notes that I wrote a few years ago. It's kind of like a chapter in a textbook that you can find on T-Square. And that will hopefully, that combined with this lesson and what we do in class will hopefully help you understand and master the concept of degree of freedom. It's a very powerful thinking tool. And it's something you really have to get mastered to move through this course and do as well as you would like. And of course, it'll serve you well in other courses and really throughout life to be able to understand what information is missing. Do you have enough information to solve it? And so it's really important to think about those things first before you jump right in and start crunching numbers. All right, take care. That's it for now.